Welcome back to this introductory lecture on proofs. In this fifth segment, we will introduce a new proof technique called a trivial proof. Like the previous technique called the vacuous proof we discussed in the fourth segment, this proof technique applies to theorems that are stated as conditionals. P implies Q. Now remember that a conditional is true whenever its conclusion is true. In other words, in this case, as soon as Q is true, regardless of the truth value of P, the whole conditional is true. And that is the fact that we use to apply the technique called trivial proof. So a trivial proof of a conditional P implies Q basically boils down to proving that Q is always true. Now that's not always applicable, but whenever Q is always true, that's the easiest way to prove that the conditional P implies Q is true. So as an example, let's consider the propositional function P of n, where the domain for the variable n is again the set Z of all the integers, positive, negative, and 0. And let's look at the particular definition of P of n. It says for all A, for all B, where we assume, for example, that the domains for A and B is the set of real numbers. If A is positive and B is positive, then it must be the case that A plus B to the power n is greater than or equal to A to the power n. So we're not going to try to prove P of n since P of n is not a proposition. But as our third theorem in this lecture, we're going to prove that P of 0, which is a proposition, is true. So to make sure we agree on what P of 0 stands for, it's obtained by plugging in the value 0 for n in the definition of P of n. So P of 0 states that for all A, for all B, if A is greater than 0 and B is greater than 0, then A plus B power 0 is greater than or equal to A power 0. So let's start writing the proof for this theorem. Now before we write anything, we should think about the strategy we want to follow. And in this case, the crux is to realize that this proposition here, the conclusion of the conditional, is always true. We're going to prove that in a minute, but first you need to realize that this proposition contains two variables, namely A and B. And that the overall conditional is universally quantified for A and B. So in other words, what we need to prove is that this proposition is actually true for any possible value of A and B. So the first step is to remember the domain for the variables A and B. And we said the domain was the set of real numbers. Since we are trying to prove a universal statement, we're going to pick two arbitrary values for A and B. So let's say let A and B be any two real numbers. Now usually we use a bar over the name of the variables to remember that what we're dealing with is a specific value, but one that we don't know anything about, that we chose arbitrarily. So from now on, I'm going to probably drop the bar over the variables as is typically done in mathematical proofs. But just remember, A and B from now on are two arbitrary real numbers. And now we can start writing the proof. So the first step is to realize that A plus B to the power 0 is equal to 1. That is an axiom of arithmetic. Secondly, A to the power 0 is also equal to 1. Any number to the power 0 is equal to 1. So as a third step, we can put together the two previous propositions to infer that A plus B to the power 0 is equal to A power 0, since they are both equal to 1. But if two numbers are equal, as in proposition 3 here, then it means that the first one is greater than or equal to the second one. Being equal, two numbers being equal, is a stronger condition than the first number being greater than or equal to the second number. So make sure you are convinced that proposition number 3 does imply proposition number 4. But what we just proved is that for any two arbitrary values of A and B, this proposition is true, and that is the conclusion of the conditional. In other words, we can now conclude that the whole conditional is trivially true since we proved that its conclusion is always true. And remember that to conclude our proof, we use this symbol here. And this concludes this segment.